Welcome to this explainer. Today, we're diving straight into an absolute evolutionary arms race between humans and parasites, and the high-yield pharmacological weapons we use to fight back. Whether you're prepping for boards, rounding on the wards, or honestly just fascinated by medical biology, this visual syllabus is going to lock these concepts right into your memory. Here's our roadmap for today. We'll start with the antiparasitic arsenal, move into weapons against malaria, then cover starving and paralyzing worms, defeating protozoa and leishmania, some crucial exam pearls you absolutely need to know, and wrap up with a rapid-fire finale. All right, let's kick things off with Section 1, the antiparasitic arsenal. While vaccines and vector control, like bed nets and bug spray, definitely play a huge role in global health, our chemical arsenal is just completely unmatched when it comes to direct clinical control. But it's a really delicate balance. Rising costs, driven by drug resistance, counterfeit medications, and clinical misuse, are constantly threatening our upper hand. That's exactly why understanding how these drugs work is more critical now than literally ever before. Moving right along to Section 2, weapons against malaria. Now, check out this breakdown. Our chemical weapons fall into distinct classes based on exactly how they attack. Take the 4-aminoquinolines, like chloroquine. They work by sneaking inside the parasite and inhibiting heme polymerase. This essentially causes the parasite to drown in its own toxic heme. Brutal, right? Then we have the artemisinin, like artesunate, which are a full 10 times more potent than other antimalarials. They combine with iron to create a massive burst of lethal free radicals that just shred parasite proteins. It's highly targeted biological warfare. Want to know how crazy effective these are? Just look at this number, 600. Chloroquine accumulates an incredible 600-fold higher inside the parasite's acidic food vacuole compared to the human plasma. It essentially hijacks the parasite's own digestive system to concentrate the poison. Okay, this is where it gets really interesting because our arsenal has some wild quirks. Artemisinins have such an incredibly short half-life that we are forced to combine them with longer-acting partner drugs just to prevent the infection from bouncing back. But my absolute favorite detail here? Atovaquone. When Plasmodium mutates to become resistant to atovaquone, that very mutation makes the female parasite completely sterile. It brilliantly stops resistant strains from transmitting. And for sheer firepower, look at pyronerdine, clocking in at 100 times more potent than chloroquine. No joke. Let's pivot to Section 3, starving and paralyzing worms. Yep, the tactics get a bit visceral here. So first up in this category are the benzimidazoles. This is a staple class of antihelmintic drugs with names you've probably heard: albendazole, mebendazole, and thiabendazole. These agents essentially win the war against nematodes through a highly targeted strategy of cellular starvation. Let's walk through this literal cascade of doom for the nematode. First, the drug binds directly to the parasite's free beta tubulin. This immediately stops microtubule polymerization. Without those microtubules acting as a cellular skeleton, the parasite's entire structure collapses, which completely blocks its ability to take up glucose. The end result? Starvation, death, and expulsion of the worm. Boom. But wait, contrast that slow starvation strategy with ivermectin. Ivermectin goes completely the opposite route. It binds to glutamate-gated chloride channels that are specific to invertebrates. This causes a massive flood of chloride ions, leading to hyperpolarization and complete flaccid paralysis of the worm's pharyngeal muscles. So we're either starving them out or paralyzing them so they can't feed or attach. Next up, Section 4, defeating protozoa and leishmania. The secret sauce here is exploiting biology that the parasite has, but we don't. Take pentavalent antimonials, our frontline defense against leishmaniasis. These specifically target trypanthione reductase. Now, humans use glutathione for our antioxidant defense, but these parasites, they rely entirely on trypanthione. By targeting an enzyme we don't even possess, we hit a perfect biological bullseye. Guys, the stakes with African trypanosomiasis are literally life and death. If you catch it early, you use suramin, which is a large compound that doesn't cross the blood-brain barrier. But if the central nervous system is involved, you're forced to use melarsopril. And here's the scary part. Melarsopril crosses the blood-brain barrier, but it comes with a terrifying 6% risk of reactive encephalopathy, which itself carries a roughly 50% case fatality rate. It is a drastic, last resort measure for a truly dire situation. All right, we are entering the danger zone. Section 5, crucial exam pearls. I need everyone on high alert for this one. Never, and I mean never, mix halofentrine and mefloquine, or even give them within 3 weeks of each other. The combination causes a severe, synergistic, and very often fatal QTc prolongation. This is a classic high-yield board question and an absolutely vital clinical warning for your future patients. Now, what about the liver? Drugs like chloroquine and artemisinin do absolutely nothing against the dormant intrahepatic hypnozoites of Plasmodium vivax and ovale. For those, primaquine and tefenoquine are completely essential. But, and this is a massive but, mandatory G6PD testing is required before giving these 8 aminoquinolines. If you skip this, you risk triggering severe, life-threatening hemolysis in deficient patients. It's actually kind of beautiful how safe some of these drugs can be when they hit the right target. Definitely memorize these. We've talked about trypanothonium and those invertebrate chloride channels for ivermectin, but also make sure to note phosmidodomycin, which targets the non-mevalonate isoprenoid pathway in Plasmodium. Because humans completely lack this pathway, the toxicity to the host is remarkably low. Almost done. Let's bring it home with Section 6, our rapid-fire finale. Things in antiparasitic pharmacology used to move at a snail's pace, but just look at this timeline. Recently, we've seen a massive surge of FDA approvals. In 2018, we got tafenoquine, moxidectin, and benznidazole. Then by 2020, artesunate and nifurtimox for children hit the US market, while older, super-toxic mainstays like sodium stibogluconate were globally discontinued. The whole field is evolving so rapidly right now. Take a mental screenshot of this rapid-fire numbers table, because memorizing these figures will absolutely save you on the warts. For instance, knowing albendazole needs the 28-day on, 14-day off cycle for prolonged tissue infections is vital to avoid crushing the patient's bone marrow. Also, check out tefenoquine's massively long 2 to 3 week half-life. That drastically improves patient compliance compared to remembering a pill every single day. Actually, if your head is spinning with numbers right now, just anchor this one in your brain, 28. It's the number of days you keep a patient on albendazole before giving them a rest period, and historically, it was the standard 28-day course required for pentavalent antimonials and meltofosine to overcome resistance. It pops up everywhere. So that brings us right back to our foundational quote here. While the pharmacology is incredibly complex, requiring strict monitoring and a deep, deep understanding of unique parasite biology, chemotherapy remains our ultimate shield in this ongoing biological war. Which leaves us with this huge question. As parasites rapidly evolve resistance to our current arsenal, literally forcing us to combine drugs and carefully monitor every single dose, what completely unknown parasite-specific pathways will our next generation of drugs need to exploit to keep us safe? It's an absolutely fascinating medical frontier. Thanks for joining me on this explainer. Keep reviewing the information on these slides and stay curious.